Alright, hello everybody. Welcome back. Um, today we're going to be talking about proofs. So, I know many times before you've seen many theorems or some mathematical statement and you've had to prove it, and sometimes you did, sometimes you didn't. Usually you've proved it by using something called brute force. Brute force, really, is just doing the algebra, manipulating it, and getting something that you don't know into something that you do know, but algebraically in that sense. So today we're going to be talking about two more methods, and the next video, or maybe a video I've previously recorded, something like that. In another video we're going to talk about the last method of proving something. So this video we're going to be talking about two types of proofs. They consist of something they consist of something called a contradiction. So I'm sure some of you math enthusiasts have probably heard this before but don't know it, or maybe you do know it. I don't know, but a proof by contradiction. So that is basically just where it's kind of like it's usually to prove for things like existence and stuff. They're not usually used to prove that those identities or stuff like that. They're mainly used to prove existence of things, like the proof that E is irrational, or the proof that there are infinite primes. The proof that there are infinite primes is very common. And there's a good video on number file on that. So I'll let you watch that one, because but today we're going to be talking about a less common proof, which is the proof that E is irrational. So we're not going to be doing it the way Euler did it. We're going to be doing it a different way. So this is for existence, right? Yeah, and we're going to prove it in a second, but before that I want to talk about the other method. So the other method is gonna be the other method is gonna be on what you call that? Induction. Mathematical induction, I love it, but this is usually for set conditions. And there are two steps in this. First step is very easy, the second step is really hard sometimes. The problem with induction is that you need to know, and it's kind of the same for contradiction, is that when you prove something, you should you have a set goal to go to. You're not like finding it out. You probably either know that the answer is something, or like, I know that E is irrational, that's why I can prove it using contradiction. But if I didn't know it, I can't prove it by contradiction, because it's nothing I'm trying to approach to. And induction is where the two steps. The first step is the base case. The base case is where plug min, and that's where you see what is this? Okay, you just plug in the minimum. Like, let's say the set conditions are like prove this expression with n, x, or whatever, and and induction is usually for only one variable, not for two or more. Sometimes it can be for two or three, but yeah. Like I was saying, when like there's a minimum, like n has to be greater than or equal to 4, then the minimum would be 4. So that's the base case. You just plug in that number. You just plug in the base, right? And then the next thing, the next step is a little harder. It's plug variable, like plug the variable equals like some constant k plus 1. So obviously, with the variable, if you plug it in for, let's say, k, then it's obviously gonna work. But to prove it, you need to do k plus 1. So that means that if it worked for the base case, then it'll work for k plus 1. So what that means is that, let's say you had some statement, and it's true for, now this is the base case where it starts, and then now there's 1 for, then you can plug in the next thing, the next thing, the next thing, and so on and so forth, right? You can keep plugging in every number. So this is, so like, yeah, so this is the base case, right? And then this is a base plus 1. So actually, now let's think of some notation. This is B1, or actually I call it B now because it's the base case. This is B1. This is the base case plus 2, or the base case, or B1 plus 1. Right. This is B2 plus 1. This is B3 plus 1, and so on. So now you notice that if it's true for the base case and it's true for k plus 1, then you can do this plus 1, you get this. If it's true for this, you can do that plus 1, you get B2. If that's true, you can plug in k plus 1, you get B3, like that. And you keep doing that, and then it just goes to infinity. And then that means that it'll be true for everything from the base to infinity. So yeah. If you don't understand it, hopefully you'll understand it when we do an example. But first, we have to do contradiction. So I'm going to be proving that E is irrational. So if you don't know what E is, I think I talked about it in my algebra 2. At this moment, the video is not out yet, but it will be soon. So yeah, E is just, you just need to know it's a special number, and it occurs in finance and math and stuff like that. But you don't, I'm sure you guys don't know this. Most of you don't know this. Some of you will, but E can be represented as an infinite series. If you don't know what an infinite series or series is, algebra 2 again. And then I'm going to talk about something called factorials, which again, and not algebra 2, but go to counting probability for that one. But you learned this in, I think, calculus with the Taylor series, but until then, it's just a cool mystery kind of thing. So E can be equal to 1 over 0 factorial, where 0 factorial is 1, plus, and then after that, it's just everything else, right? So 1 over 1 factorial, plus 1 over 2 factorial, plus 1 over 3 factorial, plus dot dot dot. E is approximately 2.71828 something something something. So notice that this is 1 plus 1, which is 2, and then everything else would be the 0.71828 dot dot dot. This comes up with the fraction part. So in other words, this is the floor of E, and this is E minus the floor of E. I can't really read it, so the floor of E, and this is E minus the floor of E, which is equal. Oh my god, which is equal to fractional part of E. I know this is yeah, but it talks about that. You guys will learn that in algebra 2 again. But yeah, hopefully at this point you have an understanding of the previous topics, which consist of basic number theory and algebra and counting probability, stuff like that. So yeah, and then if I would write that in a sigma notation, again algebra 2, you'd write it like this. I'm not going to use n. Okay, there you go. So now I'm going to be proving that E is irrational. So what does irrational mean? I'm not gonna go over the definition, but I mean I am. But so first of all, an irrational number is anything that can be expressed as p over q, where this number is an integer and this number is a whole number. Or sorry, not a whole number, because then it consists of 0. This is a natural number. What this means is that q can be 1, 2, 3, 4, so on, and p can be anything between any like it can be negative, it can be anything below, like, okay, so it can be -3, -2, -1, 0, 1, 2, 3, dot dot dot, anything, and dot 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 in the other direction from -3. So yeah, so if that's an irrational number, then an irrational number means something that cannot be like this. So just remember that. I'm gonna write that like here now. So p over q, this is integer, and this is natural. Okay, so now we have that, and now I want to go over what a contradiction is. I know I'm stalling kind of, but yeah. So a contradiction is a proof where you prove the existence of something. So in this case, we're proving that the existence of its irrationality, I guess. So what you do is, I'm gonna scroll back up here. You assume opposite, right? That's why it's only for existence, because then there's an opposite. But if there's not, but if you're like proving some formula, then you can't. There's no opposite. Inverses do not count. So assume opposite, and then what you do is you're crazy, and so you prove that this is false / impossible. And you're gonna see what I mean when I do the proof. So what we're doing is that we're assuming the opposite. So we know that it's irrational. So we're gonna assume that it's rational, and then we're gonna prove that if it was rational, then there's gonna be some crazy statement. For example, a simple one is like, I'm some crazy man okay, I know that 0 is not equal to 1, but I have this crazy statement that 1 is equal to 2. And so I say, prove me wrong. And you tell me, no, you're an idiot, 1 is not equal to 2. So I say, no, 1 is equal to 2. So if you were doing contradiction, this is what you do. You say, okay, say that 1 is equal to 2. You just assume this. Okay, you know it's not true, but just assume it. And then what you do is you say that if that is true, and you subtract 1, some algebraic manipulation in this case, we're subtracting 1 on both sides, you get 0 equals 1. But you're gonna say that I just said that 0 is not equal to 1. So how can 0 equal 1? Thus, this is not equal to 2. And I say, oh, okay, cool. If the opposite of false, it removes that option, so it can only be the other. So now we're gonna apply that here. So remember that q is natural, and notice that all these numbers are natural, right? So that technically means at some point we're gonna find 1 over q factorial, right? So yeah, and also we're trying to say that e is equal to p over q, right? We're using a contradiction, so we're gonna say e is rational. So we're gonna assume e is rational. So p over q, where p over q is e, is equal to 1 over 0 factorial plus 1 over 1 factorial plus dot dot dot. And at some point we're gonna find a q, right? And then goes on to infinity. Now we're gonna subtract everything until 1 over q factorial on both sides, and we're gonna get p over q minus 1 over 0 factorial minus 1 over 1 factorial minus 1 over 2 factorial minus dot 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 minus 1 over q factorial equals 1 over q plus 1 factorial plus 1 over q plus 2 factorial plus dot dot dot. So now what we're gonna do is we're gonna multiply by q factorial on both sides. So right? Yeah, okay. So now we're gonna multiply by q factorial, and we're gonna get pq factorial over q minus q factorial over 0 factorial minus q factorial over 1 factorial minus q factorial over 2 factorial minus dot 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 minus q factorial over q factorial. Now notice that in the first case the q's cancel and you're gonna get p times q minus 1 factorial. Here you're gonna get just q factorial. Same here. Here you're gonna get q factorial over. So actually, I'm gonna show you something. So when you have q factorial, it's equal to q times q minus 1 times q minus 2, right? Multiply everything down to 3 times 2 times 1. So notice that all of these denominators are less than or equal to q. So when the denominators are less than or equal to 2 or q, then they're gonna be in the factorial. So when you're multiplying things and you're gonna divide by 2 factorial, if you divide by 2 factorial, these would cancel. When you divide by 3 factorial, these would cancel. 4 factorial, then the 4 factorial would cancel. So every factorial until q factorial is included in q factorial. That means that we're gonna have that means that on this side minus q factorial over q factorial is 1. On this side we're gonna have a natural number, right? So it's natural. On the other side though, we're gonna multiply by q factorial. We're gonna get q factorial over q plus 1 factorial plus 1 q factorial over q plus 2 factorial dot dot dot. That's equal to and then now we're gonna see some more cancellation. We're gonna get 1 over q plus 1 plus 1 over q plus 2 times q plus 1 plus dot dot dot. And we know that q is natural, right? So that means that q is at least 1. So yeah. So that means that if q is at least 1, then if you plug in 1, we're gonna get 1/2 plus 1 over wait, am I doing this right? Yeah, okay. You're gonna get 1/2 over yeah, and sorry, before I plug in 1, I'm gonna say that this is approximately or less than, obviously, but less than like q plus 1 times q plus 1 and then q plus 1 times q plus 1 plus q plus 1. So instead of q plus 3 times q plus 2 plus q plus 1, we're gonna have q plus 1 times q plus 1 times q plus 1, right? And that would be less than. Notice that also when you do this and then you plug in 1, it'll also be less than again. But less than means just less than. So we're gonna have less than. When you plug in 1, you're gonna get 1/2 plus 1/4. Wait. No, sorry. Oopsies. Q plus 3, q plus 1. Yeah, okay, so now you're gonna get q plus 2. 3 times 2, that's 6. Yeah, okay, so now when you plug in 1, actually before I did that, I was supposed to plug in 2 or 1. You get 1 over 6 plus 1 over plug in 1 again to the next one. You're gonna get 4 times 3 times 2, and that's gonna get you to 24. So now we're just having all the factorials, and now that is also less than 1 over 2 plus 1 over 4 plus 1 over 8 plus 1 over dot dot dot, right? Because 1/6 is obviously less than 1/4, 1/24 is less than 1/8, and everything beyond that is less than whatever terms here. So now this is much easier to deal with our geometric series, right? So now we have a natural, and then here when you plug no from our geometric series, this is just equal to 1/2 over 1 minus 1/2, which is equal to 1. And we can actually show that geometrically. We take a half, and then after that we take a fourth, then an eighth, then a 16th, and so on, right? And we keep coloring this in and in and in and in, and then at one point we might as well just say that it's all covered in. So it's just 1. We'll just move. Okay, yeah. So that means that we can technically just so if you have A is less than B is less than C, then we have A is less than C, right? So we're just moving the B technically, because yeah. So in this case, I like to deal with this, the second one, much more. So I'm just gonna say that we have a natural less than and then in this case you can, it doesn't have to be 1, right? You can do 2 and it's gonna be bigger. If you do 3, it'll be bigger, so on. So it's, and then this number is gonna be, or wait, no, sorry, if you plug in 2 it's gonna be smaller, if you plug in 3 it's gonna be smaller. So this is all let's say some number j, and it's between 0 and 1, right? And we could equal 1 in this case. So we have a natural that is equal, or like, yeah, we have a natural that is equal or less than or whatever between 0 and 1, so j. But naturals have to be greater than 1, so it can't be less than j. And now we look, j is between 0 and 1, so that is impossible to do. And because that's impossible, there's nothing you can do. So so we were trying to prove that E is rational, P over Q. But we got a false impossible statement. This is false and impossible. So if this is never gonna be the case, then we were trying to prove that E is rational, and because that's impossible, this is never gonna be the case. We saw that we have a natural between 0 and 1. That's not possible. So this is never possible. So E is not rational but irrational. Now that was the main proof I wanted to do in this video. I got that from the German Fox. Yeah, although he did it more interestingly, but yeah, yeah. So now we're gonna do induction. Induction is gonna take a lot less time because I'm only proving something like that big. It's a smaller proof. Induction is usually for variables, when you have like something with a variable, right? So now we're done with contradiction. Now induction. So maybe in counting or algebra or whatever, you might have learned that 1 plus 2 plus 3 plus dot 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 plus n equals n times plus 1 over 2. Now I'm going to prove this using induction. Now you know this, right? And that's why we're going to prove it using induction. And we're not going to be doing the old method where you take 1 and n, 2 and n minus 1, and they're all going to end up to be n plus 1, and then you have n over 2, so n plus 1 times n over 2. We're going to prove it a different way. So what we're going to do is we're going to, so induction says, remember I explained that earlier, so we can just do it. We do the base case. So what's the minimum value of n? Well, 1, right? Because it can't go 1 to 0 or 1 to negative 1. It can go 1 to 1 though. So you plug in 1. for n, and you're gonna get 1 equals, you plug in 1 for n, you get 1 times 2 over 2, or 1. So that's obvious. So we did the base case. Now this is the harder part. We plug in the variable k plus 1. Now I'm sure some of you were confused when I said that. So when you plug in k plus 1 for n, you're gonna get 1 plus 2 plus 3 plus dot 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 plus k plus 1 equals, you plug in k plus 1 for n, you get k plus 1 times k plus 2 over 2. Notice that all of this is just k plus 1, or k times k plus 1 over 2, and then plus, we have a k plus 1. You can find a common denominator, you get 2k. Actually, I'm going to expand this first. So, yeah, you expand that, and k times k plus 1 is k squared plus k. And then we find a common denominator, we get 2k plus k, right? Or 2k plus 2, sorry, over 2. And that's equal to, you expand that, you get k squared plus 3k plus 2. I just added 1 and 2 to get 3, and multiply 1 and 2 to get 2. And then you divide by 2. This becomes this. And then there's 1, 2. And then multiply by 2 on both sides because it's just a constant. And then now you simplify the left side, and you're going to get k squared plus 3k plus 2 equals k squared plus 3k plus 2. And that's true always, right? Because they're the same thing. Now, obviously, you can subtract k squared plus 3k plus 2 on both sides, and you're gonna get 0 equals 0, which is more obvious, but yeah. So now we did a simple one, but yeah, and we're also gonna do the same thing for 1 squared plus 2 squared plus 3 squared, so on, and yeah. So I'm sure you might have heard of 1 squared plus 2 squared plus 3 squared plus dot 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 plus n squared. Actually, I'm not sure you have, but maybe you have. I don't know. Probably not. Probably have. And that's going to equal to n times n plus 1 times 2n plus 1 over 6. So now, how can we prove that? The problem is that if you didn't know this, you can't really use induction because you didn't know that this is true. But yeah. So you do this. How can you use induction? You plug in n equals 1 again, right? You get 1 squared, or 1 equals 1 times 2 times 3 over 6, or 6 over 6 equals 1. So that's true. Base case is true. Now the harder part, variable k equals k plus, or n equals k plus 1. Now in this case, it's going to be a little harder than last time. You might have thought, oh, that was not that hard. But this time it's going to be harder when you plug in k plus 1. So, because you're going to get 1 squared plus 2 squared plus dot 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 plus k squared plus k plus 1 squared. So now this isn't just k squared plus 1 squared. This is k squared plus 2k plus 1. So you're going to have to expand it. And that equals, you plug in k plus 1 here, it gets even uglier. You get k plus 1 times k plus 2 times k plus 1 times 2 is 2k plus 2 plus 1 is 2k plus 3 over 6. Now I'm going to expand on the right side, and I'm going to expand on the left side and do this substitution. We're going to get, and I'm actually going to write this part in expanded form. Yeah, so k, so notice that this is equal to, we expand this, you get 2n cubed plus, you're going to get 3n squared plus, plus, n, yeah, over 6. So now you plug that in for k right over here, and you get k cubed, or 2k cubed plus 3k squared plus k over 6 plus k squared plus 2k plus 1, and find a common denominator for 6. You get 2k plus k squared, so 6k squared plus 2k becomes 12k plus 1 becomes 6. equals, and then you expand this side, you get 2k cubed. This part's a little harder. Plus, what are the squared terms there? It's gonna be a 3k squared, right? Plus 3k squared is gonna be a 4k squared, 7k squared, then, and there's also gonna be a 2k squared, so 9k squared, I think. Plus then we're gonna have what are the k terms? I could easily just say that this is equal to the left side, but I want to try to like go through it and yeah, show it. Now, what are the k terms? There's gonna be 6k. There's gonna be yeah, okay. There's gonna be 6k. There's gonna be 3k, 9k. Then there's gonna be 4k, 13k. Then you're gonna add the constant term, which is just 6 divided by 6. This is equal to, right, multiply by 6 on both sides. So now you're gonna do some things, and you get plus 9k squared plus 13k plus 6 equals, and then here we're gonna have 2k cubed plus 9k squared plus 13k plus 6, and they're equal, right? So that's good. Yeah, subtract this on both sides, you're gonna get 0 equals 0, but yeah. Now, one more thing I want to do before I end this video is gonna be 1 cubed plus 2 cubed plus 3 cubed plus 4 cubed, so on to n cubed. Now, I like this one a lot because it's really cool. I saw this when I was in something grade, that one, yeah, so it was like plus 2 cubed plus n cubed equals 1 plus 2 plus 3 plus n. You can say that this is equal to n times n plus 1 over 2, and then you square both sides, and you get what you want. Equals n squared times n plus 1 squared over 2. And that's equal to n squared plus 2, n plus 1, so n to the 4th plus 2n cubed plus n squared over 2. Now we need to prove that this is true. So this one we can't really prove using induction. I mean, we could, but I'd rather prove this one because it's more familiar territory and we know what to do with this one. So we're gonna do this. Yeah, and when you plug in and when you do this, then it's gonna, we can work backwards and we're gonna get this first one, which I like. The first one is really cool, but the second one's more, you can actually apply the second one. Let me just, okay, so we have 1 cubed plus 2 cubed plus n cubed equals n times n plus 1 over 2 squared, and that's equal to n to the 4th plus 2n cubed plus n squared over 4. So now we plug in the base case, n equals 1. We're going to get 1 cubed equals 1 to the 4th is 1 plus 2 to the times, and 1 to the 3rd, 1 squared, all 1. So 1 plus 2 plus 1, or 4 over 4, and that's going to be 1. So that's true. Now the harder part, this time is going to be a bit harder. So we're going to have 1 cubed plus 2 cubed plus dot 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 plus k cubed plus k plus 1 cubed equals, plug in k plus 1 here, you get k plus 1. Oh god, I don't want to do it to the 4th. So I kind of like this one more. So I'm going to do that. So we're going to do k plus 1 times k plus 2, and we're just gonna keep this form for now until we can and then we're gonna expand this numerator, and then we're gonna do it, oh no, to the fourth, god, to the second, and then we're gonna expand it, and then yeah, when we expand the top and square it, it'll be a lot easier. So now here we have k to the fourth. Now I'm writing it like this because later I said that we're gonna expand this and then we're gonna do squared, and then we're gonna get some k to the fourths and stuff like that. So it's better we just do this now. Plus k plus 1 cubed is, and then that times 4 is gonna be 4k cubed plus 12k squared plus 12k plus 1 over 4. Now we have the common denominator. We can just do like that. Just add them. Boom goes the denominator. Becomes just one of them. And then here we have k squared plus 3k plus 2 over 2 squared. And now that is equal to, we square the top, we get k to the fourth plus 9k squared plus 4 plus 6k cubed plus 4k squared plus 12k over 4. Multiply by 4 on both sides, you get this. Simplify the right side, you get k to the fourth plus 6k cubed plus 13k squared plus 12k plus 4. And we multiply by 4, right? And then now, we simplify the left side, we get k to the fourth plus 6k cubed plus 13k squared plus 12k plus 1. Oh, it's not even writing perfectly aligned. Right, and now we take a quick check, and they're not equal. Did I miss something? Yeah, okay, that's equal to k to the fourth plus, okay. Oh yeah, sorry, when we multiply by 4 on this one, this was 4. Right, okay, so now here we're gonna have 4 too. And now, there we go. So, there we go, nice. Now, this is true, so there we go. So that means what we were trying to prove is true. So now I want you to try something. First of all, I want you to check out why they're infinite primes, and I want you to try to look, why is it that like, I want you to look deep into these two, see why they work really. I know I explained them, but I want you to kind of discover them. And I also want you to do one more thing. Oh my god. I also want you to do one more thing. I also want you to try to do induction or contradiction for something that's obviously false. Like, for example, I did 2 0 equals 1 thing with contradiction. Think of another one, think of some examples, do some examples, stuff like that. If you see something that you won't need to prove, didn't do it. These things will come in handy a lot when you go to USAMO, IMO, stuff like that, Putnam, because their questions are more like prove this, prove that, not rather than solve this. So yeah, thank you for watching, and I'll see you guys in the next one. Goodbye.